organizers. You're all awesome. Thank you so much. Yeah, I'm doing research, as Megan said. I'm doing research at the Astronomy Department at the University of Washington. I study how galaxies form and evolve. And today I'm excited to share with you some progress that has been made recently in the field of dwarf galaxies. Yeah, and that's what I'm going to talk about. As you heard, Andy's not here, so you're going to hear about galaxies for like forever now. Megan basically a couple of minutes ago said you have no time limit, so I don't know, 9 p.m., 10 p.m., whatever. Okay, cool, let's start. So I'm going to talk about dwarf galaxies and galaxies in general, but I want to start with this image of the clear night sky, something that's often challenging in Seattle. And most of the objects we can see on the clear nights outside the city is stars, right? Stars in our own galaxy, in the Milky Way. There are a couple of objects here that are not stars. Do people know what they are here? Planets. Excellent. What planets?
Jupiter, Venus.
Okay, Jupiter is good. Venus is not here. But yes, we have.
Sorry.
It's good. We have Jupiter and Saturn here. So that was good. What's the other object that's not a star here?
Earth.
Yes, Earth is here in the picture. Another object.
Andromeda.
Andromeda is not here, but another galaxy is here. It's the Milky Way. Okay? So again, most of the objects, most of the points of light in this image are stars in our own galaxy, the Milky Way, stars that produce energy and emit it as light. Usually most of the energy is emitted as visible light that we can see with our eyes and our telescopes. There are a couple of planets here, and there is this band, brighter band, which is the Milky Way around our own galaxy. Okay? And our galaxy, if you view it from the outside, it's a spiral disk galaxy. This is obviously an illustration. We don't have yet an image of the galaxy, of our galaxy from the outside. But since we're inside this disk, we're viewing it as a bright band across the sky, right? Another galaxy you can see nearby, which was also mentioned earlier, is Andromeda M31, our largest galaxy neighbor, which is kind of on the side, so you can see it as a disk. Okay, cool. So another thing we need to know for this talk about galaxies is that our universe is kind of weird. Most of the matter in our universe is not ordinary matter. Ordinary matter that makes up tables, us, beer, everything here is only 1/6 of the matter content or the total mass of matter in the universe. The rest of the matter is in the form of dark matter. It's kind of a silly name. It's kind of embarrassing. We don't really know what it is yet. Otherwise, we probably had a better name for it than dark matter. But that's what we know now. This dark matter makes most of the mass. It's called dark because it doesn't emit radiation, doesn't absorb radiation, so we can't see it. But we do know that it exists by its influence on ordinary matter, like stars, through its gravitational force, right, attraction. So this is one important thing, and this is important for galaxies because, like most of the universe, our galaxies are made mostly of dark matter and 1/6 ordinary matter. And this is an illustration of our galaxy again. And the dark matter halo in our galaxy that makes most of the matter is in this extended blue halo in this illustration. And most of the ordinary matter is concentrated in the center. This is the disk of stars and gas and dust that you can see, we saw in the picture earlier. Okay, so now that we know how galaxies are built or what they're made of, kind of, we can continue on to what's new in astronomy. So as I mentioned, there has been a lot of progress in astronomy over the last couple of decades. And I want to talk a bit about what's new. So on the observational side, what we started doing in the last couple of decades is large sky surveys. So what's a large sky survey? If you want to make one of those yourself, what you need to do is take a decent sized telescope like this one. This is a 2.5 meter or 8 feet telescope at Apache Point Observatory in New Mexico. It's a very nice telescope. Once you have the telescope, you can use the wonderful conditions at that observatory to observe the night sky. Hello. Awesome. That's very exciting. Cool. That's a good age to start, I think. Yes. Yeah, so once you have the telescope, you can start taking pictures of the night sky, pictures like this. Different from the last picture I showed, most of the objects or points most of the objects in this picture are not stars, they're galaxies, very, very distant galaxies, similar roughly to our own Milky Way galaxy, with hundreds of billions of stars in them. And this image covers only a very small fraction of the sky. It's a very small area. So you need a lot of these images, okay? So you observe one night, 1 month, 1 year, several years probably, and you can start constructing a map of the sky. So this specific survey, the Sloan Digital Sky Survey, which started in the 90s, covered a fairly decent amount or area on the sky, about 1/3 of the total. This is the area that is mapped. And once you have these maps and all these images, you can start constructing maps of the universe. Other than this two-dimensional map, we have distances to galaxies, and we can start putting them on this map, okay? And this is a pretty exciting thing that emerged, again, out of the survey in the 90s. This is a map of galaxies in the nearby universe. Every point here is a galaxy, and you can see the map basically traces the large-scale structure of matter or galaxies in the universe. Okay, you can see that some parts are denser here, for example, or here. Some are less dense. These areas are blocked by our own galaxy, so we can't see them as well. But we have a very nice map of the nearby universe. And this is very, very impressive. Okay, we can start really understanding how the universe looks like, what it's composed of, and a lot of interesting insights. And these surveys that started in the 90s are very, very impressive achievements, right? You have to build this telescope. It has to perform well over several years. You have to analyze a lot of data that you accumulate over the lifetime of this survey. And then you have to analyze it, correct for errors, and construct these maps. Okay? One last thing I want to note about this specific survey is that one of the partners in the survey was the University of Washington, the Astronomy department, and the survey is still running in its different phases. Now I think it's went into its 5th phase with slightly different goals than the initial survey. So the telescope is still being used for science. So this is on the observational side. I want to switch gears to the theoretical side. Okay? On the theoretical side, one of the most significant advances in the last couple of decades was large cosmological simulations. So let's say a few words about this. The basic idea behind these large simulations is taking the equations of the physical processes that we know about the universe, how we understand the universe works, write them down, write some code that solves these equations, put it in the computer, and let it solve it, run as a function of time, for example. Now, just to illustrate things, we know for some time now that the gravitational force between two masses or two objects depends on the masses of these two objects and weakens with the distance between them, right? So this is fairly simple, and for two masses, it's definitely fairly simple. But as you increase the number of bodies you want to simulate, planets, stars in the galaxy, different galaxies in the universe, it becomes complicated pretty fast. So running these on your laptops is probably not the best idea, okay? And what's used for astronomical large simulations are supercomputers like this one, the NASA Pleiad supercomputers with thousands of cores, a lot of memory, a lot of storage space. Even on these supercomputers, large cosmological simulations take several months to run, okay? But what we get out of this is a simulation of how our universe evolves with time, okay? Can we click on the link on the left circle there, please? Awesome, thanks. So what we're going to see is a short movie of the illustration of the simulation box and how it evolves, how our universe, simulated universe, evolves with time. Okay. But again, just the point is that we're simulating the whole universe for its entire lifetime, as we know now, about 14 billion years. And the simulation traces how an initial uniform distribution of matter falls and evolves into galaxies, clusters of galaxies, stars, planets, etc. Oh, maybe we should start it. I'm not sure. It did start, or? Okay. Okay, cool. Thanks. No worries. So you can see the time of the simulation here. And this will show, sorry, this box will show the evolution of dark matter in the universe, the density of the matter in the universe. Remember, this is most of the mass, and this is the gas temperature. So dense points will show where galaxies are, where clusters of galaxies are, etc. Okay? And the main thing to see here is that the universe starts with, again, a roughly uniform distribution of matter and evolves into this structure, which is called today the cosmic web. These knots and filaments that connect the knots. Clusters and galaxies are in these densest regions. And you have this web-like structure. Okay? I think we can go back again through this circle in the corner. Awesome, thanks. So this is the result of such one such simulation, the illustrious project. And you can see, again, this result of the cosmic web. Okay? And again, these simulations, similar to the sky surveys, are very impressive achievements, right? You have to write very efficient code for these supercomputers, run this for a while, and then take the data coming out from the simulation and analyze it and hopefully get some insights into how we understand nature and physics. So let's see how the observations and the theoretical simulations agree or disagree with each other. So these are, again, maps of the sky. Each point is a galaxy. You can see the large-scale structure of the universe in the nearby universe. And what's impressive is that two of these slices, or two of these maps, any two of these maps, are simulations. And two other maps are from observations. And the interesting thing here is that these maps are very similar, right? Now, they're not similar to the level of, this structure is here, it has to be here too. But in the sense of that statistical properties, the general distribution of galaxies and matter in the universe are similar between the maps. Okay? For example, you can see this kind of wall structure here, and there's one here too. You can see this here and here too. So, the conclusion from this, or what this means, is I think is very deep, right? It means that the observed universe that we see, that we measure with our telescopes, and the simulated universe that we create in our computers or supercomputers are in agreement with each other. So this means that we actually understand something in our models that we put into the computers about the real complex universe. Okay? So that's an amazing achievement to me. This is, to me, it's mind-boggling. And again, it couldn't have happened without progress on both of these fronts, both the observations and the theory. And this is really impressive. Of course, if everything agreed very well, we could have stopped the talk here. I might have been out of a job. It's not the best outcome. So it works to some extent. Okay? And where things break down is dwarf galaxies. And this is what I want to talk about next. So at this point, I mentioned dwarf galaxies a couple of times. Let's see how they actually look like. Okay? So you've seen a galaxy like this in one of the previous slides. You've seen the picture of Andromeda. This is another galaxy, NGC 4414. The phone number is not super important, but it has about 1 million stars, 100 billion stars in it. And again, it's a very nice spiral disk galaxy. A dwarf galaxy looks like this. Okay, so this is Leo T. It has by a factor of 1 million less stars than NGC 4414. And if you're asking where the galaxy here is, that's a fair point. Okay? Most of the things in this picture are not the galaxy. They're foreground stars in the Milky Way. For example, this is a star, this is a star, this is a star, this is a star. Most of them are stars in the Milky Way. The galaxy is here. Okay? And you might agree with me that it's not as impressive maybe as this galaxy, right?
Yeah.
No? Sorry?
Can I ask a question?
Yes, of course.
So how do you define a galaxy? Is it a galaxy is when there's a black hole in the middle and everything's orbiting it? Is that what a galaxy is?
That's a very good question. I was hoping for it to appear later in the talk. But the easy answer would be to say that there's dark matter halo around the galaxy. And that's how we know there's a galaxy there. And if you ask how we know there's a dark matter halo, then I would say the same way we know there's a dark matter halo here, which is the velocity of stars in this region, right? The way we know there's dark matter halo both here and here is the velocities of stars we measure are higher velocities than we expect from the mass of the galaxy of the stars themselves. So there's more mass there that we don't see. This mass basically holds the galaxy together and defines it as a galaxy. And we can talk more about this later if there are more questions. This is a very rich topic of discussion. By the way, I encourage questions throughout the talk because at some point I might get bored of listening to myself talk. Yeah, so this is dwarf galaxies. This is Leo T. Even if it's not super impressive at first sight, it's a very interesting galaxy, and we'll get back to this. And one of the challenges in finding these dwarf galaxies is just finding them, right? So analyzing data to find these very faint objects, a millionth of the number of stars than here, right? Finding this is easy. Finding this is not easy. So that's the first challenge. And once we found them in these large sky surveys that emerged from the 90s, we found some pretty interesting stuff. And this is what I'm getting to, I promise. So one of the revolutions of large sky surveys was in our understanding of the local group, which is again related to dwarf galaxies, and this is what I want to show now. So the local group is basically our neighborhood in the universe, our small group of galaxies. And the classical picture of the local group is this. You can see the two galaxies you know well by now, the Milky Way, Andromeda, and a couple of small satellite galaxies. Milky Way has large and small Magellanic Clouds, which are visible from the southern hemisphere. Andromeda has a couple more. But in this classical picture, there are about 10 galaxies in the local group, right? Today, we know that there are more than 100 galaxies in this neighborhood of the Milky Way. And this is, again, mostly due to these large digital sky surveys. So you can see, again, this is Milky Way here in a reverse to confuse the audience. This is Andromeda. And you can see each of them has more than 30 satellite galaxies. This is a factor more than a 10-fold increase. And this by itself is very interesting, right? Even our closest neighborhood in the universe is not what we used to think it is, right? This is a very different picture, right? I think one of the questions in the trivia session was whether dwarf galaxies are the most abundant in the universe. And here, it may have not been clear, but this is very clear. Dwarf galaxies are very, very abundant in the universe. And this may also seem like a very impressive number, right? 100 galaxies, this is nice, it's a fairly nice neighborhood. But apparently, if you ask simulators or theoreticians, this is not enough. Because if you simulate the area of the Milky Way, then this is what you get. Okay? And this is, in this simulation, this is a dark matter only simulation. Each bright spot or dot or blob is a dark matter halo, and presumably, in which presumably a small or larger galaxy can form. Okay? So the central region here is the Milky Way, so we're simulating roughly this region. But I think you'll agree that there are a lot more halos here than here. Okay? And there's often this joke about astronomers that, you know, a factor of 2 or a factor of 10 is not important, maybe. Sometimes calculations are not very accurate. This is a whole other discussion we can have later. But this is not a factor of 2 or 3 discrepancy, right? This is a factor of more than 100 discrepancy. This is serious. And another way to say this is serious is that this problem got a name in the 2000s, the missing satellites problem. And a lot of papers and a lot of conferences were held to address this problem. This is how you know it's serious. Okay? And the two basic options are either saying that we're missing something in observations, right? Because these dwarf galaxies are very faint. We need large telescopes. We'll always need larger telescopes. Analyzing these big data volumes and finding very faint galaxies is difficult. So maybe maybe all these halos are there from the simulations, but we're just not seeing them for some reason, right? That's one scenario. And the other option is that the theory, the equations we're putting into the simulation are missing something. Something we misunderstand about the universe, and all these halos are just not there. Okay? So this is the problem that dwarf galaxies have introduced into our lives. And as often the case in physics and science, there's no single answer or solution. What I want to do for the last part of the talk is discuss a few possible solutions, okay? Which I think are interesting. I hope you'll agree. So the first option, or the first scenario, is that the dark matter halos in the simulation never should have formed. Okay? And this goes back to the properties of dark matter as we understand or really don't understand them. Today, one of the leading scenarios or one of the leading theories about dark matter is that it's another particle that we just didn't find yet. We know that ordinary matter consists of particles such as electrons, protons, neutrons. So maybe there's another particle that we haven't found yet that makes up the dark matter, that for some reason doesn't interact with radiation, and that's why it's dark. And one interesting thing is that the properties of this hypothetical particle are very important for formation of galaxies and structure in the universe. For example, on the left, you can see a simulation with a certain set of properties for the dark matter particle, which are called cold dark matter. This is the standard scenario today. And this is a pretty similar picture to what we saw earlier that introduced the missing satellites problem. But if you change the properties of dark matter slightly to be slightly warmer or have higher temperature, we won't go into the details of that, you get this picture, which is very, very different, specifically in the number of subhalos or dwarf galaxies that form. Okay? Now, I think this is really interesting, not because of the specific problem necessarily. That's interesting too, in my opinion. But I think this is really interesting because this is a classical physics setup. Because now what we can do is reverse this problem and say we can count the number of galaxies in the real universe and constrain or say something about the properties of the dark matter particle, right? If we know that the real number of dwarf galaxies in the universe is closer to this number, then we can rule out this scenario, maybe, right? And I think this is a very powerful idea. So this is one option. Another scenario is that the dwarf galaxies, small galaxies formed, but somehow were destroyed. Now, if you ask what process can destroy a galaxy, an entire galaxy, that's a good question. And there are at least two mechanisms that can do that. One mechanism is internal, processes inside the galaxy that can destroy it. And here, the mechanism is supernovae, explosions of massive stars that eject matter and energy into the galaxy and can, for a massive galaxy, so this is an image of a supernova remnant in the Milky Way. This is a shell of hot and ionized material that expands out of the star that died. And here you can see the effect of supernovae on the galactic scale. And you can see that this is the galaxy, right? This is the disk of a galaxy, M82, if you're interested. But these outflows, or this haze here, are winds driven by supernova explosions of hot gas, expelling gas and dust from the galaxy, and basically starving the galaxy, this large galaxy, from forming future stars by expelling this gas. Now, for massive galaxy, supernovae or supernova-driven winds can prevent star formation, but for a smaller galaxy, they can actually break it apart or tear it apart. So this can be very significant. A second mechanism for breaking a galaxy apart is external. In this picture, you can see interaction of two massive galaxies passing by each other in close proximity, and through gravitational forces or tidal forces, tearing gas and stars from each other. And you can see both galaxies have these tails of gas and stars trailing behind them. Okay? So again, in this case, these two massive galaxies will probably survive, but smaller galaxy might not. Oh, this is amazing. Thank you. Yes, so much better. Awesome. Thank you. And we actually have an example of this process, of this mechanism happening in our own Milky Way. So this is a view of the sky. In this picture, this is the galaxy. This is the Milky Way. But here you can see on the sky a smaller galaxy. The large Magellanic Cloud is here, and the small Magellanic Cloud is here. And they're both galaxies that are falling or accreting onto the Milky Way. And you can see here too that stars are being torn away from the large Magellanic Clouds away. And this is a trail of gas that's also being ripped out of these galaxies by the gravity of the Milky Way. So again, both internal and external mechanisms can destroy small galaxies. The third option, it didn't work till now, did it? Okay, I'm not sure this is better. Put this away a bit. Okay. Let me know if this is okay. The third option I want to discuss is slightly less dramatic than breaking galaxies apart, but it's very interesting, again, to me personally. So, and the basic question we can ask here, we know that we saw already that there are large galaxies in the universe, and there are smaller galaxies in the universe. And we can ask how small a galaxy can be, right? This has 100 billion stars. This one has 100,000 stars. Can we find a galaxy with 1,000 stars, 100 stars, maybe 1 star? And this goes back to the question that was asked earlier. And maybe the more important question for the missing satellites problem is if these dark galaxies exist, how can we find them and observe them, right? So this is the problem we're going to tackle in the last scenario. And the interesting thing is that we can actually observe galaxies with very, very few stars, or maybe even without stars at all. And the way to do this is observe the gas that stars form out of rather than the stars themselves. Okay? We know, so again, maybe take a step back. We know that stars form out of clouds of gas. We have examples of this in the Milky Way. For example, we know that the Orion Nebula is a nursery of star formation in which young stars are born. This is a cloud of gas that's illuminated by the massive young stars in the central part here, also here and here. So we know that stars form out of gas clouds. And this much less impressive collection of blobs is observation of gas clouds outside of our galaxy in radio wavelengths. Okay? And what was interesting about this very unimpressive collection of blobs is that at least one of them was found to be an actual galaxy, right? So Leo P. Again, the contours here show the radio observations tracing the hydrogen gas in these galaxies, or in these clouds, sorry. But at least one of them was found to be a galaxy, and you can actually see the stellar population here in the center. And you can see that it's much less, it's much less extended than the gas cloud in this galaxy. So why again? So first we have a method of finding galaxies with very little stars in them through their gas content. And why is this interesting for the missing satellites problem? If many more of these blobs are actually tiny galaxies, then maybe this solves the missing satellites problem, right? Okay, cool. So through these different solutions to the missing satellites problem, we actually went through a couple of interesting things we can learn about dwarf galaxies, right? Starting from what are the properties of dark matter, what are the key processes of galaxy formation and evolution, how galaxies evolve and maybe break up or fall apart, both through internal and external processes. And eventually, how galaxies form in different environments, how efficiently, and how we can find even smaller galaxies with smaller number of stars. So I started with this title, but actually really think that a more appropriate title would be that dwarf galaxies provide us with a wealth of opportunities to study very different things, both about astrophysics, cosmology, and even maybe particle physics. So they're amazing. So one option is to stop here. And another option is to say a few more words about how we find more dwarf galaxies in the future, but maybe we can take questions first. Yes. I'm sorry, yeah. Excellent. Okay, thank you. This is a very good question. So should I repeat the question or yes? Okay, awesome. If the question was, the very interesting question was, if the galaxy has no stars, what's the definition of a galaxy, right? Cool. So again, this goes back to the question that was asked earlier. This is a very interesting question, a very rich question. There's a lot to say about this. Around like 10, 15 years ago, there was a lot of discussion on this question exactly. And you can take you can look at this from different angles. But if you look from the point of structure formation and galaxy formation on cosmological, on the scale of the universe, then the easy answer would be that if it has a dark matter halo around it, then it's a galaxy. And it's a very good point because I think it was and maybe still is difficult for people to accept the point whether a galaxy without stars is really a galaxy or not. And I think the other challenge that comes with it is, although I presented a very a somewhat optimistic prospect of saying we can find these gas clouds and maybe they're galaxies. The problem is that without finding the stars in these galaxies, it's much more challenging to measure distances to them. And through these distances, we also measure their masses, their luminosities, all the important things that help us decide whether there's a dark matter halo there and whether it's a galaxy. So the problem is complex. But from a purely, let's say, theoretical point of view, if it has a dark matter halo, even if it's just filled with gas with no stars, it can still, at least by some people, defined as a galaxy. This was a very long answer to a short question. Yes. It's hard to hear, so if you can come closer, I'm sorry.
So why could the simulation see the external like ripple part of them?
The external what?
Like the dwarf galaxies being like accreted by the big galaxies. Why could the simulation see that?
Why couldn't or could?
Couldn't.
Accreted, you mean disrupted, or accreted like falling onto?
Like you gave the three scenarios of why the simulation.
Right. Yeah.
One of them was that they were being like destroyed.
Yes.
By
Yes. Okay. Oh, thank you. Yeah, so the question was why the simulation couldn't see the dwarf galaxies accreted onto the large galaxy being disrupted or destroyed, right? Okay. Yeah, so that's a good question. There are again a couple of aspects to it. So gravitational forces are definitely included in the simulation. Some of these simulations are dark matter only simulations, which make comparisons to things we observe challenging, clearly. Since then, we've ran simulations that also include ordinary matter, which are much more complex because the physics of ordinary matter are much more messy because of radiation and hydrodynamics and whatnot. In these simulations, both in the dark matter simulations, we see small halos being disrupted. In simulations that include ordinary matter, we also see them being disrupted, and often more easily, because the inclusion or the presence of matter changes the distribution of matter in the galaxy. So we definitely see that, and to some extent it does alleviate the tension with the first generation of simulations. So yeah, so that helps to some extent. Yes? I'm sorry, I can't hear at all.
I think I've read that we think that most of the dwarf galaxies around Milky Way will be absorbed eventually by the Milky Way.
Right.
That's number one.
Okay.
Number two, do we think that most of the galaxies in the universe also have a sphere of dwarf galaxies around them?
Okay.
Number three.
Oh, wait. Okay, it's a lot.
Number three is if there are clumps of dark matter, what is causing those clumps to form? Is there a gravitational thing that's happening there?
Yes.
That causes them to form?
Okay, so I'll choose two.
Okay.
I'm sorry. Yes, so there were two other questions here. One is whether we think that other galaxies in the universe have spheres or populations of dwarf or satellite galaxies around them. The answer is definitely yes. How many satellite galaxies parent or large galaxy have is an interesting question. That's an open question in research. And the other question was how clumps of dark matter form. So the answer to that is easy. It's the gravitation, right? I said that dark matter doesn't interact with radiation. It doesn't have gas pressure in the simple sense of that we're familiar with. So it's all gravitation. Yeah. Yes, there was a question here and then there.
How do you differentiate a dwarf galaxy from a globular cluster? Is it that the
Oh.
globular is gravitationally bound by baryonic matter only? Is that the key?
Okay,
or-
that's the third part of the question that I was expecting to hear.
Okay.
Awesome. Okay. Okay, so now there was an advanced question of how we differentiate between a globular cluster and a dwarf galaxy. And this really completes the set of questions of what defines a galaxy. So this is very nice. And the answer is, as I think the question, yes, as was also suggested in the question, is that, as I said, dwarf galaxy is defined by the dark matter halo that confines it, whereas today we understand that globular clusters don't have these dark matter halos. So again, for example, one interesting question is whether globular clusters are dwarf galaxies that were stripped from their dark matter halos or not. The answer is probably not, but that's, again, we don't really understand globular clusters, so that's another problem. Yeah. There was another question here, and this will be the last one.
Using that definition about the dark matter halos, are you detecting dwarf galaxies within the Milky Way?
Oh, okay. Yes, okay. Thanks. Yes, so the last question was whether we detect dwarf galaxies within the Milky Way. So this is interesting because this kind of goes back to the question of how we define a galaxy. If we define a galaxy, let me go back a bit. If we define a galaxy as this, as this central part, as the disk of stars and gas and dust, then the easy answer would be no. By the point that dwarf galaxies have fallen all the way in, they're probably disrupted completely or almost completely. Okay? If you choose to define a galaxy as this entire structure, including the dark matter halo, then definitely, as I said earlier, we know today that there are about 20 to 30 dwarf galaxies in this volume, accreting or infalling into the dark matter halo of the Milky Way in different stages at different times. That said, I want to mention that the Gaia telescope has made very interesting progress in this aspect because it mapped a lot of stars and measured a lot of their properties, which allowed us to reconstruct different structures, both inside the Milky Way and in this volume. So we can see actually streams of stars, presumably from disrupted dwarf galaxies that were accreted onto the Milky Way halo at different points in different stages of disruption. Some are more compact, some are more disrupted, some are older, some are younger, which is really, really interesting. And there are people, I think, here who can address this in more detail from the department. Thank you. I think this was, yeah, I'll be happy to talk after, but this will stop here. Okay.
Is the offer still on the table to say a few more words about dwarf galaxies?
Yes.
What do you have to call it encore?
Okay, thank you. This is a lot of fun, all the excitement. Thank you. Yes. So I want to say the future of the dwarf galaxy is really the future of how we find more dwarf galaxies and how we study them. It's not really the future of the dwarf galaxies. They'll be disrupted. Let me get there. Yes. So yeah, so as I mentioned, I think one of the challenges, at least on the observational side, is finding dwarf galaxies and studying them. Because, as I mentioned, to find them, we need large sky surveys that are very sensitive because they're faint. And then to study their properties, we need to really observe them for longer times to measure better the properties of, for example, individual stars in these galaxies, because those tell us about the properties of dark matter halo, for example, and the ages of the stars, and all kinds of interesting things. So the way forward would be first big sensitive surveys. So as I mentioned, in the 90s, there was a Sloan Digital Sky Survey, and now is a very exciting time, both at the University of Washington and for astronomy in general, because next year we'll have first light on the next generation of a large sky survey, which is the Vera Rubin Observatory in Chile. So this is the structure of the telescope. We can talk a bit more about it in a minute. So that's one crucial step in finding more, in conducting more sensitive sky surveys and mapping our universe better, and specifically finding fainter dwarf galaxies out to larger distances in the nearby universe. The next challenge, as I said, is to study these galaxies once we found them. And for that, one very interesting, very exciting thing that's going to happen in the upcoming decade is the construction, or finishing the construction of the extremely large telescope. This is a European project, also built in Chile. Today, the largest telescope, the largest optical telescopes on Earth have mirrors that are about 30 feet in size, about 10 meters. This is a telescope with a mirror of 30 meters over about 100 feet. So about a factor of 3 in size, in diameter, about a factor of 10 in the light collecting ability, which is very, very significant. And the third thing, which is related to the third scenario I mentioned of observing gas clouds and finding unformed stars, in a sense, is another big project, which is the square kilometer array. You can see kind of a motif here. Astronomers are not very good at naming things. It's kind of embarrassing, but it is what it is. So the square kilometer array is a radio telescope, which is not even a single dish telescope, as opposed, for example, to this optical telescope. It consists of a large number of smaller radio dishes collecting radiation, collecting radio waves. And it's going to be very, very sensitive, have very high resolution, so we can learn a lot about hydrogen, which is the most abundant element in the universe, and star formation in different environments. So all three very different telescopes, very different projects. All of them are very exciting for different areas, for different science goals. Each of them is about a $1 billion project. Maybe this is even more. This is, as I said, this is a US project built in Chile. This is also built in Chile. This is an international collaboration built in Australia and South Africa. And really the final part will be, and then I'll stop, I'll promise. I can say a few words about the Vera Rubin Observatory, because this is really very exciting. This is a huge project at the astronomy department at UW. So this is a cut of the structure of the telescope. This is kind of a weird shaped building. It's not like a classical dome, it's not a classical dome like the extremely large telescope, and the reason is that this is the telescope part, but this is really a whole facility of for maintaining the telescope and housing the staff that does that. Yeah, so as I mentioned, or maybe not mentioned, the exciting part about this telescope, about this project, is that it's very close to completion. A lot of people in the department and other places are working on this now. It's supposed to see first light, it's planned to see first light sometime next year. Does somebody know when exactly? Sometime next year, it's soon. And this is an actual image from 2 years ago already. This is interesting. You can see the scale by the pickup trucks here. So this is pretty cool. You should definitely check out the website. It has a lot of stuff for outreach, education, educational materials, games, science goals, very cool images, of which I only have a few. So the first is the telescope itself. It's a 350-ton telescope, diameter of 8.5 meters, about 30 feet. This is not to scale. Okay, you can see people here. This is a person, right, to scale. And this is very roughly to scale the telescope of the previous large sky survey, which is the Sloan Digital Sky Survey. So this is about 8 feet, right? So this is a much larger machine. If you're, yes. How does this compare with James Webb, and why? Yes, thank you. Yes, that's a good question. So how it compares, the mirror of this mirror is larger than James Webb. James Webb is about 6.5 meters, which is about 20 feet. This is larger. In terms of, they have very different goals. James Webb is kind of similar in a sense to Hubble, the Hubble Space Telescope, in that it sees only a very small fraction, a very tiny fraction of the sky. This is a survey telescope. It's not supposed to stare at a specific region for a week. It maps the entire sky. And specifically for this survey, what's even more impressive is that it will map the entire sky that it sees many times. So it will basically map the sky, the entire sky that it sees every, does anybody know if 3 nights or 3 nights? Awesome, thanks. Which is amazing, okay? And I can show in a second how it will do that. Sending things to space is very expensive. James Webb cost, I said these are $1 billion projects. James Webb, just for comparison, ended up costing more than $10 billion, okay? So the approach is, if you don't have to send things to space, if you can do this from the ground, it's much better. Even if it was, let's say if it wasn't, there are even more advantages to keeping things on the ground, which is upkeep and instruments. If something goes wrong with James Webb, there is no way today to replace instruments, to fix it. Yeah, usually people in the astronomy community don't want to think about it, and there's a good reason to it, right? Hubble Space Telescope lives for like 30 years now because it was serviced 4 times by the space shuttle, right? Because it's in low Earth orbit. This is not possible for James Webb. Yeah. Construction times are different. It's a lot. Yes. So I mentioned that this is a survey telescope, and it's going to map the entire sky in 3 days, as I was told. And the way it can do this is with this amazing thing, which I'm not sure why it's not showing. Nice. Okay, no worries. Okay, so the amazing thing, one of the amazing components of the Vera Rubin Observatory is not just the telescope, it's the camera that's on the telescope. It's going to sit here, and it's a 3-ton camera. which is the largest camera ever built. It has 3,200 megapixels, which is a bit more than my camera, which is 24. And it has a huge, this camera is composed of almost 200 individual sensors, or CCDs, that form like a huge composite sensor, which is about 2 feet wide, okay? And again, the idea is imaging as much of the sky in one take. The whole design of the telescope is also very unique because not only is it big, but it's also you can move it very, very fast, exactly for this purpose of doing a fast sky survey. So you can, again, move this whole 300-ton structure at amazing speeds. And the fact that the camera sensor is so large allows it to, again, image a significant portion of the sky at once. It has a field of view, which is in diameter. It's 7 times larger than the full moon, which is about half a degree. So the field of view is 3.5 degrees. And since you have the area of the sensor, you can fit the moon for like almost 50 times across the sensor, which is a huge field of view. The field of view of Webb and Hubble are much, much, much smaller. Okay. I had something else to say about the camera. No, I think that's it. The camera itself. Never mind. Yes. So yeah, so you should definitely look for updates on this in the upcoming year. First slide, then first science result. The survey is going to run for 10 years, and this will be very, very exciting for many things in astronomy and astrophysics. So catch up on this. Thank you again. This was a lot of fun.
Okay, let's give Yakov another big round of applause.